Hi guys, welcome back to Data Every Day. Today we're looking at a data set of NYC property sales, and we're going to try to predict the price of a given property based on a series of features. So I'm just going to hop right into the notebook. We're going to be using XGBoost to make our predictions, and here I have some of the imports we'll be using today, actually all of the imports. In fact, I ended up not using those two. We'll be using NumPy and Pandas to work with the data. Then the standard scalar and train test split function from sklearn, just for pre-processing, and then we'll make our predictions with XGBoost, and afterwards see how our model's doing with an R2 score from sklearn.metrics. So I'm going to go ahead and import those, and let's load in the data using pandas.readcsv. And I can get the file path for the CSV file right over here, copy the file path, I'll just paste it in, and we can take a look. Alright, so we have 22 columns, and you can see this exceeds Pandas' limit of 20 for showing in a data frame by default. So we have this ... which means we can't see all the columns right now. So I'm going to go down to the console and type pandas.set option max columns none. And this way, when we reload data, you can see all the columns now, all 22. And we can start getting a sense of the data here. So looks like we have a few categorical columns, a good number of numeric though. So we'll have an okay time with this data set. Let's see how it goes. Let's get some information on it. This is reporting that there are no nulls in the data set. But one thing I noticed is that over here for the sale price we have this blank spot. And so it's not actually encoded as a missing value. But it looks like we may actually have some missing values in the dataset. Alright, so let's start pre-processing. So I want to do pre-processing sort of all at once. What I mean is I'm going to create a function called preprocess inputs. It's going to take in a data frame, and I want to spit back x and y, which x and y are going to be the column we're trying to predict, that's y, and x is the features, or all the rest of the data that we're using to try to predict y. So y will be df sub sale price is what we're trying to predict. So I'm just going to make a copy of it. And then x is going to be a df.drop sale price, so everything except the sale price column. So we're dropping from axis 1, and we'll make a copy of that as well. Additionally, I'd like to just create a copy of the data frame at the beginning, just so we know we're not modifying in place. We want a fresh copy that we're modifying. Okay, so currently, this function, if we pass it in if we pass our data into the function, preprocess inputs, sorry, it should be equals, and we pass in data, we should get back an x. That looks like everything except the sale price column, so we have 21 columns, and y. And this is just the sale price column. Okay, so what we can do now is keep adding sort of transformations and operations into our preprocess inputs function, and we can keep seeing what kinds of results we're getting. This way, our notebook's a little more clean, it's not so scattered, and we can always just modify the function and run it in a single line to actually apply the pre-processing. Okay, so first thing we should do, let's deal with these missing values. Alright, so right above the function, I'm going to take a look at what's going on under the hood in the sale price column. I'm going to get the unique values for sale price. Oh, sorry, this actually should be data. df is what I'll call it when it's inside the function. Outside it's going to be data. And we can see we have this entry here. It's a space, then a hyphen, then 2 spaces. So I'm going to copy that, and in the preprocess inputs function, I'm going to replace, so sale price dot replace this entry that we found. We're going to replace it with numpy.nan. So we're going to make it an actual missing value. This way we'll be able to see how many we're dealing with, because I would like to drop any entries that have missing values in the sale price column, and that's because this is what we're trying to predict. So it doesn't really make sense to fill in these values because they aren't, you know, it's like trying to predict a fabricated value. It doesn't really make sense. So I'd like to drop any entries that have this. So currently, actually, I'd like to do one more thing. After we fill in the missing values with actual missing values, I'd like to convert it into a float column, just so that we can fill it with a mean later more easily. Right, so run this, run this, run this. We can now take a look in our, actually it should be in Y now, and that did not work. Oh, I know why. I didn't actually set it equal to the new column. Like that. There we go. Okay. Now we have actual NaNs. So let's take a look at how many we're dealing with here. So y.isNA gives us trues and falses wherever there's a missing value. And we can take the sum to see the total number of missing values in here. Now there's 84,000 total rows, and 14,500 of them are missing. So if I get the mean, I can get the percentage missing. So there's 17.2% missing values. So we're going to drop 17.2% of our data. And that's basically because we are trying to predict this column that has missing values. So it's okay to drop 17%. If this were something like, I don't know, 70 to 80%, then we'd be dealing with substantially less data. Might be better to just pick a different task. But if that was the task we wanted, we'd then, I guess, have to drop all that data. So lucky it's only 17%. Alright, so df equals df.dropNA. This will drop any missing rows. As long as we specify axis equals 0, it'll drop any rows that have missing values. And then I want to reset the index afterwards. Whenever we drop rows, it's good to do that, assuming we don't want to keep the indices the way they were. And then I'm going to enable drop equals true, which keeps the old indices from becoming a new column. Alright, let me just comment this a little. Remove any records where we don't have a sale price. Okay. And this is just split df into x and y. Alright, now let's see this. We now have 69,987 rows, but still that's quite a bit of data. And we know now that our sale price column, it's actually in y, now has no missing values, just fewer examples. Okay, so what's next? There are a few columns here that are not so necessary. For example, this one, I'm not even sure what it does. Does it say anything? No, it doesn't say anything about the column. I think it might just be an ID column. We're going to drop it. So there's a few columns here we're going to drop. Let's remove unnecessary feature columns. Unnecessary / difficult feature columns. Because this is, a tutorial, I'm not really trying to go, I'm not trying to maximize the effectiveness of the model so much. A lot of these columns, they have too many values to encode in a sparse encoding. For example, I'm not sure if it would, here's a good example, address. We can be almost sure that every one of these is unique. I don't know if that's as good. How about a block? Okay, block is good. There may be some that are the same in here. Like here, you can see they are the same. But there's going to be so many unique values in here. So data sub block dot unique, and I'm going to take the length of that to see how many unique values we have in the block column. There's 11,566 unique blocks. So if we tried to encode this, one-hot encode this column, we'd have 11,566 new columns on our data set. And while we may actually have some useful information from that, for our purposes, it doesn't make sense to keep all those columns on because it's going to slow down our model so much that it's just not practical. But in a real setting, if you really wanted to squeeze out all the data that you could, all the information you could from the data, then it might be wise to keep this on and maybe encode it in a more manageable fashion. But for our purposes, we're going to drop a block, and we're going to drop any column that just has way too many unique values. So let's drop some columns. df equals df.drop, and we're going to specify, so unnamed 0, this one, we'll drop that. Neighborhood, I think borough and neighborhood we'll keep. This, yeah, we should take a look at how many we have here in each one. So there's 254. This is manageable. We can add 254 new columns on. Building class category. 47 columns, that's also manageable. Tax class at present. And very manageable. So block, this is the one that had way too many. Right, way too many. And lot, also that's pushing it, that's too many. So I'm going to drop block and lot as well. Block, lot, and let's keep going. Okay, easement. This is interesting. Why don't I do this? How about I get a dictionary that's going to map a column name to the length of unique values. Actually, we'll do it with x. X sub column dot unique, and that's for every column in data dot x dot select dtypes object dot columns. So the select dtype function allows us to get all the columns in X that have an object data type. And then we can get the column names from that and iterate through each column name. So this essentially is saying for every object column, let's return a dictionary that maps the column name to the length of unique values in that column. And actually should be select dtypes. Okay, so we can see out of all the categorical columns, how many unique values does each one have? So we were looking through these already. Block and lot are not included because technically they are numerical, so they're not showing up as object columns. But I'm just looking for anything that's really high. So address, that's way too high. Another thing I notice, easement has only one value, and it looks like it may just be white space. So easement is actually not, it's not giving us any useful information. Any column that has one value can just be dropped. It's the same as not having the column in the first place. So let's put that one on. Easement. What else? So address we can drop. Apartment number I'm also going to drop. I think there's a lot of missing values there as well. I don't see, yeah, I can't even see any apartment numbers here. Anything else? Okay, these two are interesting. Land square feet and gross square feet. These are actually numerical columns. These are not categorical. Right, they're continuous range columns. So something in these columns is preventing us from viewing them as numerical columns, because this is only targeting object columns, right? So the fact that they're showing up here means that there's some sort of illegal value in these columns that we're going to have to take a look at. And then this is a manageable amount, and the sale date, this is a date time format, so I'll create 3 new features from it, year, month, and day. But first, let's just remove these. I think that should do it. I didn't see any others that were problematic. So we're going to drop it from axis 1. And let's return and see what we get. So now this is the remaining columns. We now have 15 columns remaining. And you can see we have manageable numbers in each one except for these two, but they aren't actually categorical columns. So let's see what's going on with them. Okay. Easiest way to do this is just take the column name, land square feet, and try to convert it, try to cast it into a float column. Aha, and there we go. We have the same mysterious missing value entry that's making this a problem. So we can't convert it to a float because it has this string in it. So now that we've already dealt with this sale price column, why don't we just try filling all missing values with numpy.nan, which is an actual missing value encoding. So df equals df.replace. I'm putting in that little hyphen. I'm going to replace it with numpy.nan. Okay. Taking another look. Now we are able to convert it to a float. But we should also... Okay, so that's not a problem anymore. But let's see... So x.isNA. Let's see... the isNA is just like before. It'll have a true value if there's a missing value there. So if I sum over the rows, I can get the total number of missing values in each column. And it looks like there were a few missing values, actually a good number, in land square feet and gross square feet. If I take the mean, I can see the percent missing values. So about 30% in each one are missing. And this is pushing it. It's okay, but we're going to fill in the missing values here, all 30% of them, with the mean of each column. So let's do that here. Fill missing values with column means. So for every column in land square feet and gross square feet, first we're going to turn the column into a float column. So df sub column equals df sub column dot as type numpy.float. And then once they're floats, then we can fill the missing values. So dot fill NA will fill any missing values with a given value, and the value we want to give it is df sub column dot mean. So we're filling all the missing values with the mean of that column for each column in here, and at the end they will be floats as well. Okay, I guess we could combine this into one. I'm not going to do that. Oh, I could just take this and put it over here, but it's nicer to see them as two different statements. Okay, so let's see how that goes. Okay, so we have no more missing values. You can see we're done with missing values. And then over here, we're dealing with just a few manageable nominal columns. I don't think there's any in here that are ordinal features. At least not that I'm aware of. Tax class at present, I'm not sure if tax classes can be ordered. Might be able to, but for our purposes, we're just going to one-hot encode. There's nothing that's screaming about ordinal. But this sale date column, let's work with that a little. So let's note that sale date is encoded in a datetime format. So we can actually use pandas.toDateTime and pass in the column to convert it into a datetime. You can see dtype is datetime 64. So what's good about datetime is if we take a certain value, let's say the first value, and we can say .year to get the year. We can say .month, to get the month, and we can say .day to get the day. So if you couldn't guess already, I'm going to make 3 new columns, one for year, one for month, one for day, using the datetime format of this column. So let's up here, I'll just say get year, month, and day features from sale date column. Alright, and df sub sale date is going to equal pd.toDateTime df sub sale date. And then once it's in datetime form, I'm going to create 3 new columns: df sub year, df sub month, and df sub day. And these columns are going to be, here I'll do it this way. It's going to be the original sale date column, but with a lambda function applied. Apply lambda function that takes in, whoops, got glitched out a little. Okay, it's going to take in an x, which will be a given date time value, and we're going to return x dot, the top will have year, in the middle will have month, and the bottom will have day. So each element, which is a datetime entry, will become just a year, just a month, and just a day in the respective columns. Okay, and then when we're done, we can just drop the original sale date column. So df.drop sale date axis equals 1. Alright, let's take a look. Oh yeah, this can go. So now we have year, month, and day at the end. And the original sale date column is gone. Alright, so I think all that's left is to one-hot encode. One thing I also should note is that we want to one-hot encode zip code and borough, because these are categorical features, but they are in numerical form. So they're not showing up on this list here. So I'm just going to actually let's make numeric categorical features into string columns. So for column, there's only 2 of them. For column in borough and zip code, df sub column equals df sub column dot as type just string, as type string. Now when I look at this, I should be able to see the number of values we're getting in here. Zip code, we have 184 values, and borough we have 5. So with these columns, I'm now going to one-hot encode. So let's make a function. One-hot encode. It's going to take in a data frame, a list of columns, and a list of prefixes for each set of dummy columns that we're going to generate. So we'll start by creating a copy of our data frame. And for every column prefix pair in the zip of columns and prefixes, so zip will pair up the lists element-wise into tuples so that we can iterate through them 2 at a time. And then we're going to create a dummies data frame using pandas.getDummies. And we're going to create it from df sub column with the given prefix. Prefix equals prefix. So this dummies function, here let's just do it for zip code so we can see. So it should be X and no prefix to start. Looks like this. It takes each unique zip code, puts it at the top, and then for a given entry, you'll see we'll have a 1 wherever that zip code appeared. So here the zip code is 10009. So if we look over here, the zip code for the first example is 10009. Alright, so what we're going to do is create these dummies for a given column. I should actually note that if we have a prefix, say zip, all that means is zip will appear at the beginning of the column name so we know where they came from originally. So we're going to create dummies with a given column and a given prefix, and then we're going to concatenate together the original data frame and this new dummies columns side by side, so axis 1. Then when we're done, we'll drop the original column from which we created the dummies and return df. That's it. It's our one hot encode function. So right here, you can say one hot encode remaining categorical features. Alright, so for column in, no, actually, that's not how we're going to do it. All we have to do, because we already encoded it in a multi-column form, we just say df equals one hot encode. We're going to pass in df, I'm going to pass in a list of columns, which will just be all of these columns. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 of them. I'm just going to copy and paste it in because I just don't want to type it all out. So here they are. That's just the names of the columns here. And then prefixes. This is just whatever we want. I'll use the first 2 characters of each. This can be anything though. I'll try to make them intuitive. So BO, ZC, NE, BC, TX, BP, BS. Okay, so each one matches up to a column name, and they have to go in order. But that's it. That should one hot encode our features. So let's take a look. Alright, we have, you can see we have no more object columns, and our X looks like this. 833 columns now, but we have all these one hot columns, and everything is in numerical form. Our prediction, what we're trying to predict, is in float form as well, so we are ready to go. Last thing I'm going to do is, after we split it, I'm going to scale X with a standard scaler. So a standard scaler, let's create one, call it scaler. Standard scaler from sklearn will give each column a mean 0 and variance 1, which will allow our data to, all the features to take on a similar range of values. It will be easier for the model to deal with. So X equals scalar dot fit transform X. And this will apply the transformation to every column in X, but it actually returns a NumPy array, and just to keep it as a data frame, I'm going to turn it back into a data frame using the same columns that we had before. So columns equals x.columns. Alright, and I think we're probably done with preprocessing. Right, we can't see any more of these. So here is our scaled input. Here's what we're trying to predict. So let's begin training. Like I said, I'm going to use XGBoost today to train. So for that, well, first we're going to have to split our, we have x and y. We want to split x and y into a trained and test set. So we'll use the train test split function from sklearn, pass in x and y, specify a train size, 70%. That works well. And then we'll include a random state. This can be any number. This is just so we can reproduce the results afterwards. And we're going to store this in xtrain, xtest, ytrain, ytest. And then because we're using XGB, XGB does not support automatic validation splits, so we're going to have to create a validation set. So I'm just going to replace all these tests with val. So what I'm doing here is I'm actually going to split on the train set once. So first we're splitting on x and y and creating the train and test sets. Then we're going to split the train set further. This time specify the test size as 0.2. So 20% of the train set is going to be used as our validation set. And the remaining 80% will be stored back into the train. Alright, and then XGBoost actually uses its own data format called dmatrix, xgb.dmatrix. It's going to take in, we'll pass an xtrain, and then specify the label is going to be ytrain. And that we'll call dtrain. And then we're going to do one for each. So one for the validation. So like that, and that, val, and then one for the test. Test. Alright, so now we have our 3 data sets, and we're going to train on the train set while checking for early stopping on the validation set, and then evaluate afterwards on the test set. So for XGBoost, we need to specify some parameters, some hyperparameters. So let's specify a learning rate. How about 0.001, which is a dictionary, so like this, 0.001. A max tree depth, how about 6? And a lambda, let's give it some L2 regularization, 0.01. Okay, then our model is going to be given by xgb.train. We're training, we have to pass in the params, then we're passing in dtrain, which is our training set. Then we'll specify a number of rounds. I'm going to do it for an obscene number of rounds. I mean, I don't know if you call it obscene, 10,000 rounds, but I'm going to include early stopping. Only 10 early stopping rounds. So after the validation performance has not improved after 10 rounds, it will stop early. And let's also include the validation data here. So we pass it in as a tuple, dval, and then name is eval. And I think this is good. So let's run it. Actually, this should be round, not rounds. Okay. So you can see we are going down. It's pretty high error, high loss, but that's okay. I mean, I'm not sure how good this data is going to be for making predictions. But in either case, when we're done, we're going to get a yTrue, which will just be a NumPy array of our actual values in the test set. So I'm taking yTest, which is the answers to the test set, and I'm going to store that in yTrue. And ypred is going to be our predicted values. This will just be given by model.predict dtest. And you can see it stopped after only 44 rounds. Best iteration was 34. So we're going to create these predictions, and then we're going to compare them with the R2 score from sklearn. So I'm going to print model R squared score, and I'll use a formatted string here, 2 decimal places, actually 4 decimal places. Dot format, pass in R2 score, and we pass into that yTrue and ypred. And we have an R2 score of negative 0.0156. So this is not so great. Like, I mean, I've gotten worse ones before. Definitely, I've had R-squared scores of like negative 1,000, but it's also nothing special. You know, I'm not sure how like easy it is to guess and predict property price. I would like to improve this. So if any of you have found a better way, or a way to find substantially better results, please let me know. I'd love to learn. And yeah, that'll sum up today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.